Project 3.4.1, SAR ADC Overview and Clock. This here is the clock circuit of the SAR ADC, or the Successive Approximation Register Analog to Digital Converter. This clock circuit is made up of two resistors here and two capacitors, along with this inverter chip. There's two inverter gates used in this circuit. And it has a frequency of 10 kilohertz and a period of roughly 100 microseconds. So the easiest way to check a clock circuit, an astable multivibrator in this case, would be with an LED. We're going to see it constantly on because it's oscillating at 10,000 cycles per second, and so persistent vision doesn't allow us to see. But if we check this mirror circuit just with bigger resistor and capacitor values, you can see the oscillation right there. So there are a couple ways to confirm the claim that this is a 10 kilohertz frequency and 100 microsecond period. The first way would be with these digital meters. So first we can see on the DMM, we have 10.1 kilohertz, which is roughly 10 kilohertz. And as well on this oscilloscope, we see here a couple more things. First of all, frequency of 10.13 kilohertz and a duty cycle of 51%. Some of these measurements are going to be slightly off just due to resistor and capacitor variance in their values. And then on the oscilloscope, you can see here a fairly clean square wave, which will be ideal for cycling in our SAR ADC. As well, we can go to a Falstad diagram. This here again shows roughly 9 kilohertz. Falstad has trouble when the circuit's too fast, but that is within our accepted range. And then you can see there on the bottom, the space between the lines is 51 microseconds. So the oscillation takes roughly 2 of those lines, showing that, again, it's 100 microseconds. But there are other ways to calculate these values. So if we use the simple RC time constant for a just simple resistor capacitor circuit, which is the period is equal to R times C, we can use that for this circuit with two simple resistor capacitor circuits. The period here would be equal to 2 RC, R being our resistance value of 510 ohms, and C being our capacitor value of 0.1 microseconds. That equals out to about 2 times 51 microseconds, which again is 102 microseconds, which is our accepted period. And then using the calculation for frequency, 1 over period, we get a frequency of about 10 kilohertz, which again is within our accepted range. So that's very good. This clock, as I mentioned, is a part of a bigger SAR ADC circuit. The SAR ADC uses primarily an R2R ladder, as shown back in Project 2.1, to convert analog to digital voltages. So the first step in this conversion is taking in a sample voltage and holding that. As shown in this highlighted area, it's done by this chip. That sample voltage is whatever your input is. So, for example, it could be 2 volts, right? The ADC is going to use the reference voltage, which in this case is going to be 5 volts, but it can handle other voltages, but that'll be displayed in other projects. So say it's a reference of 5 volts, it's going to take half of that, and then it's going to compare, using the comparator at the end of that highlighted circle, the two sample voltages and reference voltages. It's going to spit out a weighting bit, either a 0 or 1, to determine whether the ADC should try a lower or higher reference voltage. So we can see on this oscilloscope here, this is from Mitsuru Yamada's site about his ADC, and the sample voltage here is 1.74 volts. So we're trying to read 1.74 volts. The reference voltage first goes to 2.5, so it's going to be half of 5 volts. We can see here that in that far left, it is higher than our straight line reference sample voltage. So our reference is higher than our sample. The weighting bit in this case is going to be a 0. So the highest bit shown by the LEDs is going to be 0. Then it's going to drop down to a quarter. So it's going to halve itself and subtract that. So it's going to go down to a quarter. And now it's less than the reference voltage. So it wants to jump back up. The weighting bit's going to be a 1. So our second most significant bit here is going to be a 1. It's going to jump back up and down until it eventually reaches an equilibrium state on that, around that 7th bit. So it's a fairly accurate circuit. Obviously, it's not going to be perfectly accurate. You would need more bits, but 7 bits does give you a fair bit of accuracy. In this case, the binary value that would be shown on these display LEDs would be a 0, 1, 0, 1, 1, 0, 0. And that's for depending on whether the reference voltage is less or greater than the sample voltage. If we take a fraction of that over 127, or just a binary 1, 1, 1, 1, 1, 1, 1, 1, and multiply that by a reference voltage, which is 5 volts, we get 1.73 volts, which is within a very good acceptable range of 1.74 volts. And then finally, if we loop back around, back to our clock here, the clock, the ADC runs on every oscillation of the clock. So the conversion is fairly fast. As we mentioned, the 10,000 cycles per second. So every cycle of the clock references, the ADC will reference the voltage, compare it, sample it, change it, and then eventually try to get closer to that sample voltage. Other than that, that's it for this submission. So thank you very much, and I hope you have a great day.